အားလုံးပဲမင်္ဂလာပါဒီနေ့ကအဲ့ဆိုရဲပေါ့နော်အပတ်စဉ်လေးလာနေကြဖြစ်တဲ့ဒီည algebra နဲ့ဟာသွားပြီးတော့ဆက်ပြီးလေးလာကြမှာပေါ့နော်ဟိုကဒီ matrix transformation ဘက်တွေအောင်ရောက်ကုန်ပြီပေါ့နော်ဒီဘက်ကိုသွားကြည့်အောင်လို့နော်
V, that is, let's say that I have some set V that is a subspace in Rn. And just as a reminder, what does it mean? That's just some set or some subset of Rn, where if I take any two members of that subset, so let's say I take the members A and B, they're both members of my subspace. By the fact that this is a subspace, we then know that the addition of these two vectors, or A plus B, is also in my subspace. And this just is our closure under addition. And by the fact that it's a subspace, we also know that if we multiply any member of our subspace by a scalar, so the fact that those guys are members of our subspace, we also know that if I pick one of them, let's say A, and I multiply A by some scalar, that this is also going to be a member of our subspace, and we sometimes call this closure under scalar multiplication. And then a somewhat redundant statement is that V must contain the zero vector, and that's true of all subspaces. V, let me write it this way. The zero vector is a member of V, and it would be the zero vector with n components here, because V is a subspace of Rn. And why I say that's redundant, because you could, if I say that any multiple of these vectors is also in V, I could just set the scalar to be equal to 0. So this statement kind of takes this statement into account, but in a lot of textbooks they'll always write, oh, and the zero vector has to be a member of V, although that's kind of redundant with the closure under scalar multiplication. Fair enough. Now, let's say that I also have some transformation T. I have some transformation T. It is a mapping, a function from Rn to Rm. What I want to understand in this video is I have a subspace right here, V. I want to understand whether the transformation of the subspace, so the transformation of the subspace, and what did we call that? We call that the image of our subspace, or our subset, either way, the image of V under T. In the last video, just to kind of help you visualize it, how did that work? Or, we had some subset of Rn that looked like this. It was a triangle that looked something like that, right? And that was in Rn. This was actually in R2. It was a triangle that looked something like that, and we figured out its image under T. So we went from R2 to R2, and we had our transformation, and it ended up looking something like this, if I remember it properly. It ended up looking like I don't remember it fully, but it was like a triangle that was skewed like this, rotated. So it was actually, I think it was more like, I think that's right. It was rotated a bit to the clockwise like that, and it was skewed. But what the exact particulars of that last video aren't what matter. What matters is that you are able to visualize what an image under transformation means. It means you take some subset of R2, all of the vectors that define this triangle right here, that's some subset of R2. You transform all of them, and then you get some subset in your codomain. And this is the, you could call this the image, call this the transformation of that triangle, or if we call this S, it's equal to the transformation of S, or you could say it's the image, of, you could call it the set S, but maybe it helps you to visualize, it's called the image of this triangle under T. Or maybe even a neater way of thinking about it is this triangle, that skewed, rotated triangle, this one is the image of this kind of right triangle under T. And I think that might make a little bit of visual sense to you. And just as a bit of a reminder, in that last video, these triangles, these weren't subspaces. And just as you could take scalar multiples of some of the vectors that are subsets of, that are members of of this triangle, and you'll find that they're not going to be in that triangle. So this wasn't a subspace. This was just a subset of R2. All subsets are not subspaces, but all subspaces are definitely subsets, although something can be a subset of itself. I don't want to wander off too much, but this just helps you visualize what we mean by an image. It means all of the all of the uh, all of the vectors that are mapped to from the members of your subset. So I want to know whether the image of V under T is a subspace. Is a subspace. So in order for it to be a subspace, if I take the transformation, let me find two members of T. Well, clearly if I take the transformation of any members of V, I'm getting members of the image, right? So I can write this. Clearly the transformation of A and the transformations of B, these are both members of our images of V under T. These are both members of that right there. So my question to you is, what is the transformation of A plus the transformation of B? And the way I've written this, these are two arbitrary members of our image of V under T, or maybe I should call it T of capital V. These are two arbitrary members. So what is this equal to? Well, we know from our properties, our definition of linear transformations, this is equal to the transformation, the sum of the transformations of two vectors is equal to the transformation of the sum of their vectors. Now, is the transformation of A plus B, is this a member of TV? Is it a member of our image? Well, A plus B is a member of V, and the image contains the transformation of all of the members of V. So the image contains the transformation of this guy. This guy, A plus B, is a member of V. So you're taking the transformation of a member of V, which by definition is in your image of V under T. So this is definitely true. Now, let's ask the next question. If I take a scalar multiple of some member of my image of V under T, or my T of capital V right there, if I take the some scalar, what is this equal to? By definition, for linear transformation, this is the same thing as a transformation of the scalar times the vector. Now, is this going to be a member of our image of V under T? Well, we know that CA is definitely in V, right? That's from the definition of a subspace. This is definitely in V. And so if this is in V, the transformation of this has to be in V's image under T. So this is also a member of V. And obviously, you can set this equal to 0. You can set this equal to 0. The 0 vector is a member of V, so any transformation of, if you just put a 0 here, you'll get the 0 vector. So the 0 vector is definitely, I don't care what this is, if you multiply it times 0, you're going to get the 0 vector. So the 0 vector is definitely also a member of TV. So we come on the result that T, the image of V under T is a subspace. Which is a useful result, which we'll be able to use later on. But this, I guess, might naturally lead to the question: what if we go? Everything we've been dealing that so far have been subsets in the case of this triangle, or subspaces in the case of V. But what if I were to take the image? What if what if I take the image of Rn under T, right? This is the image of Rn under T. Let's think about what this means. This means, what do we get when we take any member of Rn? What is a set of all of the vectors that when we take the transformation of all of the members of Rn? Let me write this. This is equal to the set of the transformation of all of the x's where each x is a member of Rn. So you take each of the members of Rn and transform them, and you create this new set. This is the image of Rn under T. The image of Rn under T. Well, there's a couple of ways you can think of this. This is, remember when we defined, let's see, T is a mapping from Rn to Rm. We define this as the domain. all of the possible inputs for our transformation, and we define this the codomain. Codomain. And remember I told you that the codomain is essentially, it's part of the definition of the function or of the transformation, and it's the space that we map to. It's not necessarily all of the things that we're mapping to. For example, the image of Rn under transformation, maybe it's all of Rm, or maybe it's some subset of Rn. The way you can think about it, and I touched on this in that first video, is, and they'll never, or at least the linear algebra books I looked at, they didn't specify this, but you can kind of view this as the range. The range of T. These are the actual members of Rm. These are the actual members of Rm that T maps to. That if you take the image of Rn under T, you're actually finding, so let me say this is, let's say that Rm looks like that. Rm, obviously it'll go in every direction. And let's say that when you take, let me draw Rn right here. Say this is Rn. And we know that T is a mapping from Rn to Rm. But let's say when you take every element of Rn and you map them into Rm, let's say you get some subset of Rm. Let's say you get something that looks like this. So let me see if I can draw this nicely. So you literally map every point here, and it goes to one of these guys, or one of these guys can be represented as a mapping from one of these guys, one of these members right here. So if you map all of them, you get this subset right here. This subset is, this is T, the image of Rn, the image of Rn under T, and in a terminology that you don't normally see in linear algebra a lot, you can also kind of consider it its range, the range of T. Now, this has a special name. This is called, and I don't want you to get confused, this is called the image of T. Image of T. It might be a little confusing. Image of T. So this is, it's sometimes written as just Im of T. Now, you're a little confused here. You're like, before when we were talking about subsets, we would call this the image of our subset under T. And that is the correct terminology when you're dealing with the subset. But when you take all of a sudden the entire n-dimensional space and you're finding that image, we call that the image of the actual transformation. So we can also call this set right here, we can call this the image of T. And now what is the image of T? Well, we know that we can write any, and this is literally any, so T is going from Rn to Rm. We can write T of x, we can write any linear transformation like this as being equal to some matrix, some m by n matrix, m by n, times a vector. And these vectors obviously are going to be members of Rn, times some Rn. And what is this? So what is the image? Let me write it in a bunch of different ways. What is the image of Rn under T? So we could write that as T, let me write it this way. We could write that as T of Rn, which is the same thing as the image of T. Notice we're not saying under anything else, because now we're saying the image of the actual transformation, which we could also write as the image of T. Well, what are these equal to? These are equal to the sets. This is equal to the set of all the transformations of x. Well, all the transformations of x are going to be ax, where x is a member of Rn. So x is going to be an n tuple with just where each element is has to be a real number. So what is this? So if we write A, let me write my matrix A. It's just a bunch of column vectors. A1, A2, it's going to have n of these, right? Because it has n columns. And so A times any x is going to be, so if I multiply that times any x that's a member of Rn, I multiply x1, x2, all the way to xn. We've seen this multiple times. This is equal to x1, the scalar x1 times a1 plus, this is x1, plus x2 times a2, all the way to plus xn times an. And we're saying we want the set of all of these sums of these column vectors where x can take on any vector in Rn, which means that the elements of x can take on any real scalar values. So the set of all of these is essentially all of the linear combinations of the columns of A, right? Because I can set these guys to be equal to any value. So what is that equal to? That is equal to, and we touched on this, or we actually talked about this in when we introduced the idea, this is equal to the column span, the column space, column space of A, or we just denoted it sometimes as C of A. So that's a pretty neat result. If you take, well, it's almost obvious. I mean, it's just I'm playing with words a little bit. But any linear transformation can be represented as a matrix vector product. And so the image of any linear transformation, which means the subset of its codomain, when you map all of the elements of its domain into its codomain, this is the image of your transformation. This is equivalent to the column space of the column of the matrix that your transformation could be represented as. And the column space, of course, is the span of all the column vectors of your matrix. Right? This is just all of the linear combinations or the span of all of your column vectors, which we do right here. Anyway, hope you found that a little interesting, and we'll be able to use these results in the future.
ဟုတ်ပါပြီတခြားလူလည်းကြည့်ရဆိုခဏစအောင်နော်ဒီကတော့အရင်တော့စိတ်မရှုပ်ပါနဲ့ကြောနားမလဲဘူးဘာဖြစ်တယ်ဆိုရင်သိရမလားသူကအဓိကပြောချင်တာလဲဆိုတော့ထုတ်ပြချင်တဲ့သဘောပေါ့နော်ဒီဟာလေးကိုမြင်လားမသိဘူးလဲဆိုတစ်ခါတော့ကလေဒီဟာပြုံးကနေကြည့်မယ်ဆိုရင်အဲ့ဒါဆိုဒီပြန်နာဒီ space တစ်ခုကနေနောက် space တစ်ခုအဲ့ဒါဆို image ကိုသွားပြီးတော့ရှာသူ့ရဲ့ image ကဘယ်လောက်ရှိလဲဆိုပုံစံမျိုးပိုပေါက်တယ်ပေါ့နော် transform ဖြစ်တဲ့အတွက် dimension တစ်ခုကနောက်တစ်ခု transform လုပ်မှာလေအဲ့လိုဆိုအဲ့လိုမျိုးလုပ်ရင်ဘယ်လိုများဖြစ်နေမလဲဆိုတဲ့ဟာပေါ့နော် properties တွေသူပြောပြတယ်ပါတယ်ပေါ့နော်အဲ့လိုလည်းကောင်းမစားနေဒီဟာအရင်တော့ကောင်းချုပ်ပြရမှာမလဲအဓိကဒီမှာ transform လုပ်တဲ့ခါကျရင်ဒီ image ကြီးကဘာကိုပြောချင်လဲဆိုတဲ့အကြောင်းလေးသူပြောသွားတယ်ပေါ့နော်သူကပြောရတဲ့စကားလုံးတွေ domain တို့ codomain တို့ဒီဟာ range တို့အဲ့ဒီစကားလုံးလေးတွေပေါ့နော် domain တို့ codomain တို့ range တို့ဒီဟာလေးတွေရင်းနှီးတဲ့စကားလုံးလေးတွေပေါ့နော်ဒီဟာအရင်နည်းနည်းတော့ရှုပ်တဲ့ concept လေးဆိုတော့လည်းအရင်ကောင်းမရှုပ်နေပေါ့နော်အဲ့မျိုးဟာဆိုဒါတော့ခုနကြည့်နေစဉ်းစားမိတယ်ဆိုတော့ဒီနေရာငါ machine learning နဲ့ဘယ်လို apply လုပ်ရင်ကောင်းမလဲဘူးပြန်စဉ်းစားနေတဲ့အချိန်မှာဒီကဘာသိထားမလဲဆိုတော့ဒီက transform လုပ်တဲ့ဟာပဲပေါ့နော်ဒီမှာဆိုရင် image ကို transform လုပ်တဲ့ခါကျရင်ဘယ်လိုလုပ်ရတဲ့ process လေးကိုသူပြောသွားတဲ့ပုံစံမျိုးပေါ့နော်ကိုယ့် domain ကနေပြီးကိုယ့် domain ကိုပြောတဲ့ခါကျရင်ဘယ်လိုလေးပြန်ဖြစ်နေမလဲအဲ့ဒါကိုပဲသူပြောချင်တာပေါ့နော်လို့ဆိုတော့အဲ့ဒီကိုယ့်ရဲ့ domain ကနေပြီးတော့ကိုယ့် domain မှာဖြစ်နေတဲ့ဟာလို့သူ image ကိုတည်လို့ခေါ်တယ်အဲ့လောက်လေးနားလည်ရတယ်ပေါ့နော်အရင်ကောင်းမရှုပ်နေ okay question လေးမေးကြချင်တယ်ဆိုဒါနဲ့ပတ်သက်ပြီးတော့လေနောက်တစ်ခုကဒီမှာသူရမ်းပြောတာဒီ transformation ကပါလဲဆိုတော့ metric နဲ့ beta product က transformation ပဲသူအဲ့ဒါပဲပြောနေခဏလက်ကြည့်နေရတော့ငါဟောက်ရှင်ရသူပြောနေဒီ transformation ကဘာပြောချင်လဲ transformation ကဘာကိုပြောချင်လဲလို့သူပြောနေတာလေအမှားဆိုရင်ဒီ transformation ဆိုတာ attribute တော့ဘာမှမဟုတ်ဘူးเนาะ beta နဲ့ metric ကိုမြောက်လိုက်တယ်ဆိုတဲ့သဘောပဲဆိုတော့ဒီကအဲ့ဒါကိုပဲပြောနေတာသူ properties တွေလည်းရှိတယ်ပေါ့နော်အဲ့လောက်ပါပဲပြန် attribute တော့ဘာမှမဟုတ်ဘူးလို့ညီမလေးမိုးနေညီမလေးမိုးနေညီမလေးထုံးခိုင်ညီမလေးသူ့ကျန်တာပြောင်းမေးနေထုံးခိုင်လေးကိုကြည့်နေတော့ပေါ့ဆိုတော့လေအဲ့ခဏသူတို့စအောင်သူတို့လေးတနာပါတယ်အဲ့ဆိုတရားဟောလိုက်သူတို့စအောင်မပြအောင်ဒီခဏသူတို့ပြန်တက်လာခဏခေါ်လိုက်မယ်နော်သူတို့စပြီးမှတူလောက်အောင်ဆိုတော့သူတို့နှစ်ယောက်ကကြံခဲ့မှာဆိုလို့နော်အဲ့လိုဆိုတော့အဓိကဒီမှာဆိုရင်ပေါ့အဓိကလက်ဒီမှာအဓိကပြောချင်တာဒီ properties လေးတွေပေါ့နော်သူမှပြောရတယ်ဒီ closure under addition တို့ closure under scalar multiplication တို့အဲ့ဒါလေးတွေအမှန်ဆိုအဲ့လိုဆိုတော့ရင်းနှီးတဲ့စကားလုံးလေးတွေပေါ့နော်ဒီဟာလေးတွေအရင်ရောခေါင်းမရှုပ်နဲ့နားမလဲလို့ဆိုတော့ဒါကိုပြောပါလားဆိုလောက်ဝတ်ထားပေးလိုက်ဒီက transformation ဆိုတဲ့သဘောတရားပေါ့နော်ကိုမှရှိရဲလဲဆိုရင် input တွေကတည်တဲ့အတိုင်းလဲဆိုရင်ဒီမှာအခုလို့ဆိုရင် machine learning မှာအကုန်လုံးသုံးတဲ့ဟာတွေကကတော့ metric တွေပဲသုံးတာလေဟုတ်တယ်ဟုတ် metric တွေကိုသုံးတာဖြစ်တဲ့အတွက်တော်တော်များများသူ့ transform က dimension ရများတစ်ခုနဲ့တစ်ခုသူ transform လုပ်ရတယ်အဲဆို GPU တို့ဘာလို့သုံးရတယ်အဲဆို metric calculate လုပ်တာအရင်ကောင်းတဲ့ဟာမျိုးပေါ့နော်အဲ့လိုမျိုးကြောက်ကသုံးနေတာဖြစ်တဲ့အတွက်သူက transformation လုပ်တယ်ဆိုတာဘာမှထွေတော့မဟုတ်ဘူးဒီ metric တွေကိုလုံးဝတွက်နေတဲ့ဟာပဲပေါ့နော်အဲ့လိုဆိုတော့ဒီဟာလေးကိုဘယ်လိုလုပ်ရလဲဆိုသဘောတရားလေးသိရင်လည်းရပါပြီနော်။နောက်တစ်ခုသွားအောင်နောက်တစ်ခုကကြတော့ဒီ preimage ဒါကြတော့ image ကိုတည်လို့ IM ခေါ်တာနော် preimage ဆိုတာပြောချင်တယ်ကြည့်အောင်ဆိုတော့ဒီဟာလေးနဲ့ဒီဟာနဲ့တွေ့ရသဘောတရားမတူဘူးဆိုတဲ့သဘောလေးမှာတော့ရှင်ဘာလဲဆိုတာကြည့်အောင်နော်
transformation that maps elements in set X to set Y. We know that we call X the domain of T, so that's my set X, and then my set that I'm mapping into, set Y, that's the codomain. We know that T is a transformation, that if you take any member of X and you transform it, you'll get, or you'll associate it with a member of set Y, or you'll map it to a member of set Y. And that's what the transformation or the function does. Now, if we have some subset of T, let's call A to be some subset of T. So let me draw A like that. This notation right here just means subset, some subset of T. We've defined the notion of an image of T of A like that, which is the image of A, of our subset A under T. We've defined this to be equal to the set, let me write it here, the set of all, or if we take each of the members of our subset, so if we take each of the members of our subset, it's the set of all of their transformations. It's the set of all of their transformations. And of course, these are going to be some subset of Y right there. So we essentially take each of the members of A. This was one of them. You find its transformation. It's that point. You take another member of A. This is all set A right here. Take another member of A. Find its transformation. Maybe it's that point. You keep doing that. Find its transformation. Maybe it's that point. And then the set of all of those transformations, maybe it's this blob right here, we call this the image of A under T. Now, what if we wanted to think about the opposite problem? What if we were to start with set Y, which is our codomain, so that's Y, and we were to have some subset of Y. Let's call our subset of Y S. So S is a subset of our codomain Y, and I'm curious about what subset of X maps into S. So I'm curious about this set. I'm curious about the set of all vectors that are members of my domain, such that their mapping or the transformation of those vectors ends up in my subset of S. So what I'm saying is, look, if I take my domain, there must be some subset of vectors. Right here, where if I take any member of this set, it will map into these guys. And that's what I'm defining right here. This is equal to that guy. So I'm literally saying, are all of the members of X where those members of X all map into S. Now, I want to make a very subtle nuance here, point out something here. I'm not saying that every point in S necessarily gets mapped to. For example, maybe there's some element in S right here, right there, that no element in X ever gets mapped to from our transformation T. That's okay. All I'm saying is that everything in this set maps to something within S right here. And what we call this set right here, the notation is the inverse T of S, but this is equal to the pre-image of S under T. So this is S, this is the pre-image of S under T, and that makes sense. The image, we go from a subset of our domain to a subset of our codomain. Pre-image, we go from a subset of our codomain, and we say what subset of our domain maps into that subset of our codomain. Now let me ask you an interesting question, and this is kind of for bonus points. What is the image of our pre-image under S? So what is the image of our pre-image under S? So if we take this guy, this is essentially the image of this guy right here, right? This part right here is the pre-image of S, right here. Now if we take the image of this, we're saying if we take every member of this, what vectors do they map into? All of them are going to be within S, so they're going to map within S, but they don't necessarily map to everything within S. So this is going to be some subset of S. So this right here is going to be some subset of our original S. It's not necessarily equal to S, but it's a subset of it. And so this is, I think, the motivation for where the notation comes from. We can construct a subset of S by taking the image of the pre-image of S. You can kind of view the image and the pre-image kind of canceling out, and that's why that inverse notation was probably introduced. Now this is all very abstract. What I'm going to do in the next video is actually calculate or determine the pre-image of some subset of my codomain.
ဟုတ်ပါပြီဟုတ်ပါပြီအဲ့တော့တိတ်တော့နားမလဲပါပေါ့နော်သူဗီဒီယိုကြည့်ရကြည့်ပဲဆိုမှလည်းသူကဘာလို့အဲ့လိုမျိုးလဲ data terminology notation တွေသူပြောတာဟုတ်ပါပြီသူကဒီမှာ domain နဲ့ codomain ကိုသူ shift လုပ်လိုက်ပုံစံမျိုးရွေး trade 2တော့ဘာမှတော့ trade 2မရှိရမမြင်သွားဘူးပေါ့နော်အဲ့ဒါသူဘာအတွက်သုံးချင်တာလဲစိတ်တွေမှမသိသေးဘူးပေါ့နော်အဲ့ဒါဆို cancel လုပ်ပါနားမလဲဘူးပေါ့နားမလဲတော့နားမလဲဆိုသဘောထားပြလိုက်ပါနေ့ဗီဒီယိုသွားအောင်ပေါ့နော် Okay Preimage နဲ့ kernel okay kernel တော့စိတ်ဝင်စား kernel ကပါတယ်ဒီစကလုံးလေးကိုပြီးနောက်ပိုင်းကျရင်ခဏခဏမြင်ရမယ်ပေါ့နော်ဒီစကလုံးနဲ့ kernel ဆိုတာလေးကိုလေ machine learning မှာရန်သုံးပါတယ်လို့နော် kernel ဆိုတဲ့ဟာလေးလေဒီပြည့်ဒီ CNN လောက်တော့ဟာကြတယ်ဒီ kernel ဆိုတာလေးရန်မရှိတယ်မြင်လာကြမှာ kernel ကပါလဲဆိုတော့ CNN မှာအရန်ပါတယ်ပေါ့နော်အရန်အရေးပါတယ်ဒီ concept လေးကိုဇော်မင်းရဲ့ CNN class မှာတက်ဖို့တဲ့လူတွေလည်းနည်းနည်းသိထားနေတယ် kernel ဆိုတာလေးစကလုံးကညစ်အောင်နော် sorry ဘာလို့ခုနဟာလဲဆိုတော့ cancel လုပ်ထားတယ်ပေါ့နော်ခုနဟာလေးကိုတိတ်ပြီးတော့နားမလဲဘူး machine learning နဲ့ဘယ်လို plan လုပ်ရမလဲတိတ်မသိဘူးဆိုတော့နည်းနည်းလေးနားမလဲလို့ပဲထားလိုက်တယ်ပေါ့နော်ဘာမှမစားဘူးပေါ့နော်ကိုရီးယား
Have some transformation from R2 to R2, and it's essentially just a multiplication times a matrix, and we know that all linear transformations can be expressed as a multiplication of a matrix, but this one is equal to the matrix 1 3 2 6 times whatever vector you give me in my domain times x1 x2. Now let's say I have some subset in my codomain. So let me draw this right here. So my domain looks like that. It's R2. And of course, my function or my transformation maps elements of R2 into elements of its codomain, which also happens to be R2. I could show it mapping into itself, but for the sake of simplicity, let's draw my codomain here. And our transformation, of course, maps for any element here. The transformation of that will be an association or a mapping into R2. Now, what if we take some subset of R2? So let's say some subset of R2, and let's just say it's a set of two vectors, the 0 vector in R2 and the vector 1, 2. So it's literally, let's say it's this point, let me do it in a different color. Let's say this is my 0 vector in R2. I'm not plotting them, I'm just showing that they're in this, they're in R2, that's my 0 vector, and let's say the vector 1, 2 is here, 1, 2. What I want to know is what are all of the vectors in my domain whose transformations map to this subset, map to this point. So I want to know, I want to know the pre-image of S. So the pre-image of S, let me be careful, the pre-image of S under, this is the pre-image of S under T. And I said be careful because when you just say pre-image of something without saying under something else, it implies that you're taking, well, when you say image of something, it implies you're taking the image of an entire transformation like I showed you, I think, 2 videos ago. But when you're taking the image or pre-image of a set, yeah, make sure you say under what transformation. So we want to know the pre-image of this subset of our codomain under the transformation T. We write this as T to the, or T inverse of S. And we saw in the last video, this is all of the elements in our domain where the transformation of those x's is a member of the subset of our codomain that we're trying to find the pre-image of, right? Now what is another way of writing this? Well, this is, you can write this, is we're trying to look for all of the x's in our domain such that this vector, let's call this A, that matrix A, such that A times X is a member of S. So that means A times X has to be equal to this or has to be equal to that. So that means A times our vector X has to be equal to the 0 vector, or A times our vector X has to be equal to this vector 1, 2. This is the exact same statement as this one right here. I just made it a little bit more explicit in terms of our actual transformation, a times x, and in terms of what our actual set is. Our set is just 2 vectors. So if we want to determine the preimage, of S, so we write that T in the preimage of S under T, that set there, we essentially have to just find all of the x's that satisfy these 2 equations right there. So this equation, so we have to find all of the x's that satisfy, the first one right here is the matrix 1, 3, 2, 6 times x1, x2 is equal to the 0 vector. That's this equation right there. We need to find all of the solutions to that. And you might already recognize that all of the solutions to this, all of the x's that satisfy this, is the null space of this matrix. I just thought I would point that out on the side. Now, that's not the only one. We also have to solve this guy over here. Do that in blue. So the preimage of S under T is going to be all the solutions to this, or plus all of the solutions to 1, 3, 2, 6 times x1, x2 is equal to 1, 2. Now, we could just solve this with an augmented matrix. So my augmented matrix would look like 1, 3, 2, 6, 0, 0. And here my augmented matrix would be 1, 3, 2, 6, 1, 2. Let's put this in reduced row echelon form. So let's replace our second row with our second row minus 2 times the first row. So what do we get? Our first row stays the same, 1, 3, 0. Let me do them simultaneously. Let me solve these systems in parallel. So my first row stays the same, 1, 3, 1. And in both cases, because I just want to get the left-hand side of my augmented matrix into reduced row echelon form, I can apply the same row operation. So I'm replacing my second row with 2 times my first row. So 2 minus 2 times 1 is 0. 6 minus 2 times 3 is 0. And of course, 0 minus 2 times 0 is 0. Here, 2 minus 2 times 1 is 0. 6 minus 2 times 3 is 0. And 2 minus 2 times 1 is 0. So we get all these zeros, and we're actually done. We have both of these augmented matrices in reduced row echelon form. And how do we go back to solve all of the x1s and x2 that satisfy these? Well, you recognize that our first columns right here are pivot columns, and these are associated with our variable x1, so we know that x1 is a pivot variable, and we know that the second column is a non-pivot column because it has no 1s in it, and so it's associated with x2, and since x2 isn't a pivot column, we know that x2 is a free variable. x2 is a free variable, which essentially means we can set x2 to be anything. So let's just set x2 is equal to t, where t is a member of the reals. In this case, what is x1 going to be equal to? So here, this top equation says, let me write it. If we just kind of go back to this world right here, this means that x1 plus 3x2 is equal to this 0 here. This top line right here says x1 plus 3x2 is equal to 1. And so if we say x2 is equal to t, this equation becomes x1 plus 3t is equal to 0. Subtract 3t from both sides. You get x1 is equal to minus 3t. And then this equation, you get x1 is equal to, if we substitute x2 with t, is x1 is equal to 1 minus 3t. Now, if we wanted to write the solution sets in kind of vector notations, the solution set for this guy right here, for this first equation right there, is going to be x1, x2 is equal to what? It's going to be equal to, well, x2 is just going to be equal to t times, is just going to be equal to t. So let me just write there. So it's going to be equal to t times, x2 is just t times 1. It's just equal to t. I made that definition up here. And then what's x1 equal to? It's equal to minus 3 times t. So if I put a t out here as a scalar, it's just minus 3 times t. So this is a solution for this first equation, sum where t is a member of the reals. So it's just scalar multiples of the vector minus 3, 1. And if we think of this as a position vector, this will be a line in R2, and I'll draw that in a second. So that's the solution for this first equation. And then the solution for the second equation, how can we set this up? It's going to be, let me make sure you can see it. It is x1, x2, and let's see, x2 once again is just t times 1. So let me just write it like this. So it's t times 1. That's x2. Now what's x1? x1 is equal to 1 minus 3 times t. So if we do a minus 3, that gives us our minus 3 times t, but we need to do a 1 minus that, or 1 plus minus 3 times t. So what we can do is we can say that all the solution set here is equal to the vector 1 here. So now we have 1 plus minus 3 times t for x1. And then here we could say 0. x2 is equal to 0 plus t, or x2 is equal to t. So this is the solution set for the second equation. So our pre-image of S, and remember S was just these 2 points in our codomain. The pre-image of S under T is essentially all of the X's that satisfy these 2 equations. And let's actually graph those. Let me turn on my graphs. That makes it look a little bit messy, but let me graph it. Well, let me graph it down here. Let me copy and paste my 2 results. So then I want to paste it. So those are my 2 results. Put my pen back on. And now what I can do is I can graph it right here. So let's see. The solution set for that first equation is all the multiples of the vector minus 3, 1. So the vector minus 3, 1, minus 3, 1 looks like this. This solution, minus 3, 1 looks like this. Looks like that. That's the vector minus 3, 1. But my solution set is all the scalar multiples of minus 3, 1. This is a comma right here. Right? So if I just take all the scalar multiples of minus 3, 1, it's going to look like this. So if you take 2 times it, you're going to have minus 6, 2. So you're going to get like that. So it's going to be all of, let's see, it's going to be all of these points right here. I wish I could draw it a little bit neater, but I think you get the idea. It's going to be a line like that. That is that solution set right there. And then what is this solution set right here? It's the vector 1, 0. So we go out 1 and 0, so that's there, plus scalar multiples of minus 3, 1. So plus scalar multiples of this. So plus scalar multiples. So if we just add 1 scalar multiple of minus 3, 1, we'll end up right there. But we want to put all the scalar multiples of it because we have this t right here. So we're going to end up with another line with the same slope essentially. That's just shifted a little bit. It shifted 1 to the right. Now, why did we do all of this? Remember, what we wanted to find out is what were all of the vectors. Let me turn off the graph paper. What were all of the vectors in our domain that when we apply the transformation map to vectors within our subset of our codomain, map to either 0, 0 or the vector 1, 2. And we figured all of those vectors out by solving these 2 equations. And we were able to see that these 2 lines, and when I turn my graph paper on, they map to the points. So when these guys, when you apply the transformation, I'll draw it all on the same graph, they map, when you apply the transformation, to the points 0, 0, and to the point 1, 2, which was right here. So all of these points, when you apply the transformation, and actually all of the ones in the blue, they map to 0, 0, because they solved this top equation. All the ones in orange, when you apply the transformation, map to the point 1, 2. Map to the point 1, 2. Now, this blue line right here, this has a special name for it. And I actually touched on it a little bit before, right? Everything in this blue line right? If I call this set right here, I don't know, let's call it B for blue. This is the blue line. That's this set of vectors right here. Everything there, when I apply my transformation of those blue vectors, or if I take the image of my blue set under T, it all maps to the zero vector. It all maps to the zero vector. It equals the set of the zero vector right there. And we saw that right there. And I remember earlier in the video, I pointed out that, look, this set right here, this is equivalent to the null space, right? The null space of a matrix, is all the vectors that if you multiply it by that matrix, you get zero. So this is the similar idea here is this transformation is defined by a matrix, and we're saying what are all of the x's that when you transform them, you get the zero vector. And so this idea, this blue thing right here, is called the kernel. The kernel of T. Sometimes it's written as just shorthand, KER of T. And this literally is all of the vectors that if you apply the transformation, let me write it this way. It's all of the vectors in our domain, which was R2, such that the transformation of those vectors is equal to the zero vector. This is the definition of the kernel. And if our transformation is equal to some matrix times some vector, we know that any linear transformation can be written as a matrix vector product, then the kernel of T is the same thing as the null space of A. And we saw that earlier in the video. Anyway, hopefully you found that reasonably useful.
skip လုပ်လာတဲ့ဟာနဲ့လာတန်းထုတ်လာပြီပေါ့နော် next week ကိုအခုမှလာတွေ့တယ်ပေါ့လို့ပဲဖြစ်တတ်တယ်ပေါ့နော်အဲ့လိုဆိုတော့ဒီမှာတော့ trade ထူတော့မဟုတ်ဘူးပေါ့နော်ဒီဟာလေးတစ်ချက်ပေါ့နော်ဒီ row echelon form ပြောင်းတဲ့ဟာလေးကိုမောင်လေးညီမလေးတို့နဲ့တူတူတစ်ခါလေးဆိုလုပ်ပြပါရောလားဒီမှာ free variable တို့ pivot variable တို့ pivot row တို့အဲ့ဒါနဲ့ပတ်သက်ပြီးတော့လည်းနည်းနည်းလေးတော့ပြောတာနည်းနည်းလေးတာဝန်နာဝရှိမယ်လို့မြင်တယ်ပေါ့နော်ဆိုတော့အဲ့ဒါကိုလည်းဆိုအရင်ဗီဒီယိုတွေမှာတစ်ချက်ကြည့်ပြပါနော် free variable ကဘာပြောရလဲတို့ဒီ one တွေက pivot variable လို့ခေါ်တာလေတို့အဲ့ဒါလေးနည်းနည်းသူပြောသွားတာပေါ့နော်ဒီမှာတစ်ချက်ဆိုရင်နောက်တစ်ခုကအမှန်တော့ဒီမှာလည်းခဏခဏသူပြောတယ်ပေါ့နော်ဒီ transformation ကအမှန်ဆိုရင် metric နဲ့ vector ရဲ့ product ဆိုတဲ့စကားလုံးကိုအများကြီးသုံးတယ်ပေါ့နော်သုံးတယ်ပြီးတော့နောက်တစ်ခုက graphic ပုံစံမျိုးလေးသူလုပ်ပြသွားတယ်ပေါ့နော်မျက်စိထဲမှာမြင်အောင်လို့လေဒီဟာမျိုးဆိုတာ span လို့တော့ပြောလို့ရတယ် span ဖြစ်နေတာပေါ့နော် solution တွေအားလုံးအဲ့လိုဖြစ်နေတဲ့ဟာမျိုးသူပြောပြရတယ်ဒီမှာဆိုရင်သူဆွဲပြတာပဲဒီမှာ3-5ခုသူဆွဲပြသွားတယ်ပေါ့နော်ဒီနှစ်ခုလေးသူသေချာလေးဆွဲပြသွားဒီဟာလေးကဘယ်လိုရလဲဆိုတာဒီခုန row echelon ပုံစံလေးပြောင်းလိုက်တာပေါ့နော် row echelon ပြောင်းနေရလဲအားလုံးလိုရင်းနှီးမေးလို့မြင်ပါတယ်လို့ဒီမှာဆိုဒီ point နဲ့ဒီ point လေးသူ transform လုပ်ခါကျရင်အဲ့လိုမျိုးဒီဟာကို map လုပ်တယ်ဆိုတာ domain နဲ့ codomain စကားအတိုင်းပဲပေါ့နော်အဲ့လိုမျိုးလုပ်တယ်ဆိုတဲ့အကြောင်းလေးသူပြောပြထားတယ်ပေါ့နော်ဒီမှာလေးကဆိုရင်ဒါက solution span ပေါ့နော်အဲ့လိုမျိုးလေးရှိမယ်ဆိုတဲ့အကြောင်းလေးသူပြောသွားတယ်ပေါ့နော်ဒီမှာဆိုရင်ဟိုဘာပဲနောက်တစ်ခုကဒီမှာသူ kernel ကသူ null space ကိုပြောတာဖြစ်တဲ့အတွက်လဲဆို null space ကိုသိပြီးတော့နည်းနည်း explore လုပ်တာဖြစ်တယ်နည်းလေးကိုတွေကအဲ့လိုပေါ့နော်ခံရတယ်ပေါ့နော်အဲ့လိုမျိုးလေးဟုတ်ပါပြီ kernel ဆိုစကားလုံးအခုချိန်မှာနိုင်အောင်ငါကြောက်နာပဲထားလိုက်ရနားမလဲသေးတော့ kernel ဆိုစကားလုံးခဏခဏပြန်မြင်ရမယ်ပေါ့နော်လို့ဆိုတော့ kernel ဆိုဘာကိုပြောရလဲဆိုတာလေး kernel ဆိုစကားလုံးအခုလို့ဆိုတော့ဒီမှာကြည့်အောင် kernel ဆိုစကားလုံးလေးနဲ့ introduce ပေးခြင်းတယ်ဆို LS ရဲ့အရင်တော့ဆိုရင်ဒီစကားလုံးလေးကိုသိနားမလဲဘူးပေါ့နော် font kernel ဆိုစကားလုံးကဘာလဲဆိုရင် difficulty ဖြစ်ခဲ့တယ်ဒီဟာလေးနဲ့ပတ်သက်ပြီးတော့လေkernel က machine learning မှာဆိုရင်ပေါ့ဒီလိုမျိုး transfer လုပ်တဲ့ဟာကိုပဲသူအဓိကပြောတဲ့ဟာမျိုးပေါ့နော်ပြောချင်တာလဲဆိုဒီမှာတချို့ဟာလေးရှိပါတော့ဒီ point transfer လုပ်တဲ့ဟာကိုပဲဒီက kernel လို့ခေါ်ရဆိုသဘောလေးမှတ်ထားပါနော် simple ဆရာတွေကိုလည်းအကြောင်းကြားရမယ်ဒီကိစ္စ kernel ကဘာပြောချင်လဲဆိုတော့သူတို့တွေသိမှာပေါ့နော်ဘာလို့ဆိုတော့ဒီ kernel ကအမှန်ဆို kernel အများကြီး PCA မှာလည်း kernel ဆိုတာပါတယ်အဲ့ဒါဆိုသူ transfer လုပ်လိုက်တယ် transfer လုပ်လိုက်တဲ့ပုံစံမျိုးပေါ့နော်သူက okay kernel တစ်ခုသုံးလိုက်တယ်အခုလောဆယ် LS ရဲ့ simple example တစ်ခု LS ပြချင်kernel သုံးလို့ပါတယ် classification လုပ်တာတွေပဲရှိတယ်အဲ့လိုမျိုးတချို့ဟာလေး kernel ဆိုတဲ့စကားလုံးလေးကသူကအဲ့လိုမျိုးဘာခေါ်လဲ frontier kernel transformation မှာဆိုရင် kernel သုံးတယ်ပေါ့နော်ကြည့်ခိုင်းနော်ဒါလေးတစ်ချက်ပြချင်တယ် image လေးမတွေ့မှာဆိုလို့ဒီစီဒီခဏ test တွေပါခဏထားအောင်မလဲဆိုတော့ဒါလေးကိုဘာပြချင်လဲဆိုတော့ animal blah 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 this and that kernel apply လုပ်လိုက်တယ်ဆိုတာကဒီစီမြင်တာ expression တစ်ခုပြချင်ဒါလည်းမတွေ့ဘူးအဲ့ဆို kernel ဆိုတဲ့စကားလုံးလေးကအဲ့ဆိုရင်တော့ဘာခေါ်လဲ transformation kernel intro and practical machine learning kernel intro စကားပုံလေးဘာဥစားတစ်ခုလေးပြချင်အဲ့လက်အဲ့မှာဘယ်မှာတွေ့ဘူးလဲဆိုတော့တစ်ခေါက်လေး မှာတွေ့ဘူးလဲဆိုတော့ Alex မှာအတာကိုတေချာလေးတွေ့ဘူးလဲဆိုတော့ frontier transform မှာလည်းသတိထားမိခဏ Alex frontier transform ဖြစ်သွားလို့ frontier transform transformation ပေါ့နော်အဲ့လိုမျိုးစလုံးပေါင်း Alex မှာနေမှာ okay frontier transformation အဲ့မှာသူသုံးထားတဲ့ kernel လေးကဘာလဲဆိုရင်ဒီမှာဒါက transformation လောက်တာနော်သူ kernel တစ်ခုကိုသူသုံးထားပြီးတော့ transform လုပ်လိုက်တာဒီကလလောင်းကိုอ่ะပေါ့နော် classical method ပေါ့နော်သူဒီ frontier transform ဆိုတာကနေရာတိုင်းလိုမှာသုံးတယ်ပေါ့နော် image processing မှာဖြစ်ပါဖြစ်တော်တော်လေးများသုံးတယ်ပေါ့နော် okay ဒီ Alex အဲ့ဒါကို frontier transform ပြချင်တယ်သူဘာ kernel သုံးပြီး transform လုပ်လဲဆိုတာလေးလည်းပြချင်တယ်ငါ kernel ဆိုတာလေးမှလည်းမြင်စေချင်လို့နော် okay Alex ရဲ့ kernel ကိုပြချင်တာ okay blah blah complexity ကောက် blah blah this and that accuracy kernel ကိုရှာပါမယ် KRN ဒီမှာပေါ့နော်ဒီ kernel ဆိုတဲ့စကားလုံးလေးက transform တော့အရင် simple kernel လေးပါဘယ်လိုလဲချမ်းတွေ့တာပါလဲ kernel လေးကအရင် simple ဖြစ်တယ် okay kernel KERN okay အဲ့လေးပြတယ်ဒီစကားလုံးလေးကခဏခဏရင်းနေပြီပေါ့နော် okay using kernel smooth okay ဒီဟာလေးထည့်ကြည့်အောင်ဒါ sign ဒါလေးပြကုန်ပြီ let's go smoothing estimator kernel သုံးတဲ့ဟာလေးပြကြတယ် simple something simple let me look for it ဒါလေးရန်နေပြပါလေးမဖတ်ချင်သေးဘူးငါကောင်းရှုပ်တယ် okay အမှန်ဆိုပုံစံလေးပြချင်တာဟိုkernelနဲ့ပတ်သက်တာဒီနေ့မှာ follow ပြီးတော့ share ပေးမယ်အမှန်ဆိုဒီဟာရတော်တော်လေးသုံးတယ်ပေါ့ machine learning ရဲ့ပုံမှန်ကြည့်လိုက်ဆိုဒီ kernel ကဒီ frontier transform ဆိုတော့ kernel regression kernel ဆိုတဲ့စကားလုံးနဲ့ခဏခဏမြင်မယ်မျက်စိနဲ့မြင် image နဲ့ပြချင်တာ kernel sample kernel ပဲရှာရင်ကောင်းမယ်တဲ့အဲ့ဒါဒီဟာ frontier transform လို့ရတယ်ဆိုရင် frontier transform မယ်ဆိုတော့ engineering ဘက်ကလူတွေပုံမြင်တယ်ပေါ့နော်ဒါလဲဆိုတာ sorry sample kernel image အဲ့ဒါဆို image လေးပြချင်တယ်metric လေးတစ်ခုပါ kernel tree ထူးတော့မဟုတ်ဒါပေမဲ့သူ့ရဲ့ဒီမှာ Wikipedia kernel definition တွေသွား statistic မှာလည်းပါမယ်ပေါ့နော် kernel ဆိုတဲ့ definition တွေကမဆို apply လုပ်လိုက်လေဆိုတဲ့သဘောလေးပါဟုတ်ပါအခုလို့အဲ့ရှာမတွေ့သေးဘူး let's ပြောပြမယ်ဘယ်လိုတွေ့ရလဲဆိုတော့ဟာလေ kernel လေးတယောက်တစ်မျိုးစီပေါ့နော် frontier Gaussian data ဒီဟာလေး kernel တော့မဟုတ်တရားမျိုးလေးတွေပေါ့နော်မျိုးရှိတယ်ရှာပေးတင်တယ်ရှာမတွေ့ဖြစ်နေAlex ကိုတစ်ခေါက်သုံးပြီးတော့အကြာပြီဆိုတော့မမိတော့ဖြစ်သွားတာဒါအမှ smoothing technique တစ်ခုပဲပေါ့နော် kernel သုံးနေဆိုတဲ့ဟာ kernel ဘာ kernel သုံးပါလဲလို့ဒီ aberration kernel တွေပါအဲ့တော့ကိုစောမင်း lesson မှာလဲကိုမင်းစာအုပ်မှာလဲ kernel ဆိုစကားလုံးလေးပါသွားတယ်ပေါ့နော်အဲ့ဒါ CNN မှာပြချင်တာလေကိုစောမင်းစာအုပ်လေးမသွားရှာပဲ sorry ပါပြချင်ကိုစောမင်းစာအုပ်လေးမှာလဲတွေ့ထားတယ်ပေါ့နော်အဲ့ဒါလေးကိုစောမင်းစာအုပ်ကပမာပါလေlet's ပုံလေးခဏသိခံပါလို့အဲ့ဒါဒီမှာတင်တာပါလေကိုစော document နေမှာမလား let's ကိုစောမင်းစာအုပ်ကအောင်လားဖြစ်ပြီဒီမှာ CNN အကြောင်းပြောတော့ဟာဆိုကာနယ်နဲ့စကားလုံးပါတယ်ပေါ့နော် KERN ဒီမှာပေါ့နော်ဒီမှာကာနယ်ဆိုတာဒါလေးကိုပြောချင်တာမှန်တော့ဘာမှမဟုတ်ဒီကာနယ်ဘာသုံးပြီးတော့လုပ်မလဲဆိုပြီးတော့တစ်ခေါက်လေဒီကာနယ် filter ကာနယ်ဆိုစကားလုံးတွေ့ရဟုတ်ဒီဟာလေးကိုလည်းပြောချင်တာဒီလိုမျိုးဒီ kernel ကအမှန်ဆိုတော့ simple လေးဟာလေးပါမတွေ့ထူးမဟုတ်အဲ့မှာဒီဟာမျိုးလေးကိုမှ kernel ကဒါမျိုးပြောချင်တဲ့ပုံစံမျိုးလေးတေးလေးတစ်ခု apply လုပ်ပြီးတော့ဒါလည်း kernel မဟုတ်ဒါ feature map ဖြစ်သွားတယ် kernel လေးတစ်ခုရှိပါပဲဟို sample ပြချင်တဲ့ kernel ဆိုတာလေးကို okay အဲ့ဒါတိထားမယ်ကိုဆို main CNN လောက်တော့ kernel လေးဒီလိုမျိုး kernel လေးတွေကပါတယ် filter kernel လို့ခေါ်တယ်ပေါ့နော်အဲ့ပုံစံမျိုးလေးရှိနေoverlapping ဒီဟာက transform လို့အဲ့လိုဒါ transform လုပ်နေတာပဲပေါ့နော် kernel ကိုသုံးပြီးတော့ transform လုပ်နေတဲ့ process ပဲ CNN မှာသိသိသိရမှာပေါ့နော် kernel Android နဲ့သိသိသူပြောမယ်ပေါ့နော် kernel ကဘာလဲဆိုတာလေးကိုkernel မှာဆိုရင်သူက better metric တွေတစ်ခုပဲသူကအဲ့ဒါကိုအဲ့လို filter kernel လို့ခေါ်တယ်ပေါ့နော်ဒီလိုမျိုးဟာလေးပဲ trade ဘာမှမဟုတ်အဲ့လိုမျိုးဟာလေးကိုသူကသုံးချပါဆိုတဲ့ဘောလေးပေါ့နော်ဒီ image ကနေပြီးတော့အဲ့လိုမျိုးလုပ်ပြီးတော့ဒီမျိုးသွားလိုက်တယ် transform လုပ်တဲ့ဟာအကြားမှာသုံးလိုက်တဲ့ဟာမျိုးသူဒါ filter kernel လို့လည်းခေါ်တယ်ပေါ့နော်အဲ့ပုံစံမျိုးလေးဟုတ်ပါနည်းနည်းတရားဟောနေပေါ့နော်လို့ဆိုတော့ဒီနေ့ lesson လေးဆိုဒီမှာပဲရအောင်လေနော်ဒီဟာလည်းဆိုဒီနောက်အပတ်စပြီးတော့ CNN စလုပ်ကြရမယ်ပေါ့နော်စိတ်ဝင်စားလို့လည်း join နိုင်ပါတယ်လို့နော် okay အားလုံးလည်းကျေးဇူးတင်ပါတယ်အဲ့ဒါဆိုမေးစရာလေးရှိသေးလားအဲ့ငင်လေ hello အတန်းလေးလောက်ကြမယ်အဆင်ပြေကြတာညီမလေးတို့မောင်လေးတို့မတို့
ဟုတ်တယ်ခင်ဗျာ
hello
ဟုတ်ပြီ
ကဲပါကဲပါအဲ့ဆန်လို့ဒီနေ့ဒီမှာပဲရအောင်လေနော်နည်းနည်းလေးကြာနေပြီဆိုတော့တင်ချာလေးထားတဲ့ခေါင်းကောင်းချုပ်လေဒီကကာနယ်ဆွဲစကလုံးလေးပဲလက်မတ်မိစေချင်မှာကာနယ်ဆွဲစကလုံးကခဏခဏမြင်ရမယ်ပေါ့နော် CNN နဲ့မှာလည်းခဏခဏမြင်ရမယ်လို့မျိုး transformation လုပ်တိုင်းခဏခဏမြင်ရမယ်စကလုံးလေးပေါ့အဲ့ဒါကြောင့်လည်းဆိုပြင်ပန်းခံလိုက်ရှာပေးနေသဘောပေါ့နော်ကိုလည်းချင်နိုင်ဒီကာနယ်ဆိုတာဘာလို့နည်းနည်းရှာကြည့်ခဏပါလို့နော်ဒါဆိုအဆင်ပြေအောင်လို့လေနော်တခြားဒီmachine learning course တွေအတွက်ပါနော်ကဲပါအားလုံးလည်းကျေးဇူးတင်ပါတယ် thank you so much ပါ